What happens when we peel back the layers of modern AI and look inside the machinery? In this episode, we dive into three striking papers. One reverse engineers tabular foundation models to reveal very different hidden inference circuits behind similar accuracy. Another exposes how unreliable sparse autoencoder benchmarks can be. And the third introduces a stochastic attention design that builds uncertainty directly into the model. From interpretability to evaluation to probabilistic learning, these studies challenge what we think we know about how AI works. Let's explore the first paper, a mechanistic study of tabular foundation models. This paper reverse engineers three tabular foundation models, tabPFNv2, tabICLv2, and Mitra, on 49 classification and 10 regression datasets, and shows that similar benchmark accuracy hides fundamentally different inference algorithms. tabPFNv2 and Mitra realize a late similarity-based readout. At layer 9, tabPFNv2's query row attention becomes sharply peaked, with mean maximum attention weight 0.925, and an attention-weighted label vote matches native probabilities with Pearson R equals 0.89, forcing uniform attention drops accuracy from 0.874 to 0.488. Mitra follows the same vote family with R equals 0.89 but is not identical, because its shared per-feature embedding and label slot make column permutation exact by construction. tabICLv2 is mechanistically different. Most class structure is already readable at the column embedding output, and a parameter-free class prototype decoder on the final representation reaches 0.854 versus 0.864 native accuracy, while KNN on the final representation reaches 0.856. Cross-backbone readout transplantation fails catastrophically, losing 33 to 40 percentage points, showing the readout is jointly tuned to each backbone. The authors also identify cheap symmetry fixes, zeroing tabPFNv2's positional matrix W or removing rho P from tabICLv2 makes column invariance exact with no accuracy loss, and a 1 vers all wrapper yields exact class order invariance. Finally, mechanism-grounded attacks confirm the inferred circuits. Hub poisoning cuts accuracy by 3.3 to 3.9 points. On tabPFNv2, tabICLv2, rank warp costs 8 to 10.1 points on both, but barely affects Mitra, and SVD burial causes up to 8. 3 point drops, directly linking model failures to their learned similarity or prototype geometry. Let's explore the second paper, Are Sparse Autoencoder Benchmarks Reliable? David Channon audits SAE Bench, the standard evaluation suite for sparse autoencoders, and finds that benchmark reliability is substantially weaker than the field assumes. Using 3 lenses, 5 reseed noise on canonical gemma scope, synthetic ground truth correlation on synth SAE bench, 16K, and discriminability across 1, 5B token, and 300M token training trajectories. The paper shows that targeted probe perturbation, TPP, and spurious correlation removal, SCR, fail basic sanity. Checks at canonical settings. TPP often has 16%, 39% coefficient of variation at small top n and can worsen as training proceeds, while SCR reaches 3%, 7% CV and becomes negatively correlated with ground truth at large top n. On the synthetic panel, SCR top 500 flips to rho equals 0.64 versus ground truth MCC. By contrast, SAProbes, sparse probing, is the most reliable metric tested, with reseed CV around 0.2% and strong synthetic calibration, reaching Spearman rho equals plus 0.87 against GTMCC on Boolean INSAE tasks. However, even SAProbe saturates quickly, with top K equals 16 accuracy above 0.99 on most trained SAEs, despite GTMCC still varying from 0.56 to 0.79. Across Matryoshka variants, most non-core metrics are dominated by seed and snapshot noise. Only 7 of 34 audited scores clear a 0.2 between variance share, and canonical SCR top 10 and TPP top 10 sit near the boundary where a single seed winner is often an accident of randomness. The central conclusion is blunt. SAE Bench currently ranks SAEs reliably only when they are obviously different, so future progress needs larger task suites, more stable internal probes, and benchmark designs that reduce latent sampling and probe training noise. Let's explore the third paper, Neuronal Stochastic Attention Circuit, NSAC, for probabilistic representation learning. The paper introduces the neuronal stochastic attention circuit, or NSAC, a continuous time attention layer that replaces deterministic attention logics with the exact solution of an Ornstein-Uhlenbeck stochastic differential equation using input-dependent gates borrowed from C. elegans neuronal circuit policies. This design turns attention logics into a Gaussian process over time and pushes that uncertainty through a logistic normal attention distribution, so the model produces probabilistic outputs natively rather than via post hoc calibration. Training combines Gaussian negative log likelihood with an epistemic separation regularizer that increases variance on synthetic out-of-distribution perturbations, enabling explicit separation of aleatoric and epistemic uncertainty. Across 5 benchmarks, irregular spiral function approximation, Boston housing and kin, 8 nanometers regression, ETT1 and genoclimate forecasting, XJTUSY, pronostia, Hust-bearing prognostics, and Udacity plus OpenAI car racing control, NSAC, is consistently competitive on accuracy and often stronger on uncertainty quality. On the spiral task, it reaches MSE 0.0002 and CRPS 0.0095, outperforming deep ensembles and Monte Carlo dropout. On ETTM1, it achieves the best NLL at negative 1.3816 while maintaining reasonable forecast calibration. On XJTUSY, it obtains MSE 0.0048 and CRPS 0.0261. The key novelty is architectural. Uncertainty is embedded inside continuous time attention itself, with a closed-form forward pass that avoids numerical STE solvers and remains interpretable at the neuronal cell level. That's a wrap on today's AI paper highlights. Thanks for watching.